Okay, Module 10 is about vapor cycles, and the course outcome is the ability to acquire and explain the basic concepts in thermodynamics and how do you apply and correlate the concept with the appropriate equations and principles to analyze and solve engineering problems. By the end of this chapter, you should be able to explain, to describe the principles of Carnot vapor cycles and its impracticalities. So you need to remember what we have discussed in Carnot vapor cycles. Okay, explain the principles of an ideal Rankine power cycle. Explain how pressure and temperature affect thermal efficiency of an ideal Rankine power cycle. Explain the principle of the reheat Rankine power cycles. Sketch the TS diagram for Carnot, ideal Rankine and ideal reheat Rankine cycles, and solve problems related to ideal Rankine and reheat Rankine cycles. Okay, so the contents that we will cover is Carnot vapor cycle, what is the Rankine vapor cycle, and then we have another one, reheat Rankine cycle. Okay, what is Carnot vapor cycle? Okay, so it's kind of similar with Carnot. You used to remember about the Carnot heat engine. Okay, so it's still about the a cycle, whether it is reversible or irreversible, right? Okay, but this time it's about vapor cycle. Okay, so it is most efficient cycle operating between two specified temperature limit, but it is not a suitable power model for power cycles because why? So process 1 to 2. So look at this. This is Carnot vapor cycles. Okay, so process 1 to 2. This is TS diagram. Okay, TS diagram. What is this is temperature. This is S is actually entropy. Okay, entropy diagram. So entropy is a kind of energy similar with the enthalpy. It's a type of property like enthalpy and internal energy. So this is one of the properties in the table. Okay, we will go further for the entropy for the next module, but this is the relationship between T and entropy. Okay, so this is the curve. So starting from state 1 at here, so this is should be saturated liquid, right? 1 to 2, 2 to 3, mixture. 3 to 4 is also a mixture. Okay, so process 1 to 2, limiting the heat transfer processes to two-phase system severely limits the maximum temperature that can be used in the cycle, which is 374 degrees Celsius for water. So that's the limit. Okay, so two-phase systems. This is liquid, this is vapor. For process 2 to 3, the turbine cannot handle steam, right, with a high moisture content because of the impingement of liquid droplets on the turbine blades, causing erosion and wear. Okay, so as you can see, this is vapor. 2 to 3, we have partial of vapor and partial of liquid. Okay, so we are dealing with liquids as well, right? So it can causing erosion and wear to the turbine blades. For process 4 to 1, okay, it is not easy to control the condensation process so precisely to achieve quality at point 1. So, and it is not practical to design a compressor that handles two phases. Two phases means for this is the mixture of liquid and vapor, right? So it is not practical to use compressor for both phases of water, right? Okay, so this is the process. 1 to 2 is actually the isothermal heat addition in a boiler. Okay, 2 to 3 is isentropic. Isentropic means the entropy is constant, right? 2 to 3, the entropy is the same. Okay, isentropic expansion in a turbine. 3 to 4, isothermal heat rejection in a condenser. Okay, and 4 to 1 is a isentropic compression in a compressor. Okay, so what happened is because we are dealing with parts of liquid, parts of vapor. So we are trying to change this to this. Okay. So these problems can be eliminated by executing Carnot cycle in figure B. And okay, so however, this cycle presents other problem. Okay, we have isentropic compression to extremely high pressure if we still want to do this, because we want to make sure everything is vapor, right? Still vapor. So but in order to have this, we have problems. Isentropic compression to extremely high pressure, isothermal heat transfer at variable pressures, so it's hard to control. Okay, so conclusion is the Carnot cycle cannot be approximated in actual devices. So that one's by theoretical. So it is not realistic model for vapor power cycles. Okay, to use that. Okay, to use the original theory that we apply in Carnot vapor cycle. And so Carnot vapor cycle is not Carnot cycle is not suitable for vapor power cycles. That what does it mean? Okay, when we involve the vapor power cycles. Therefore, we are introducing ideal cycle for vapor power cycle is Rankine cycle. So this is a new cycle.